בסדר. לא, אין לי כמובן בעיה לשאול שאלות על זה. אני רוצה פשוט להתחומם. בהפסקה מי שיש לו שאלות. Okay. So let's continue. I just realized that the semester is ending soon, so I want to get to do all the things that we want to do. So we're talking about learning in the unrealizable case, and we focused on, for now, on finite hypothesis. So a finite number of hypotheses. Okay? And one of our major one of our major objects of interest was these two curves. Where one is imagine we have an axis where this is the hypothesis in the hypothesis class, and one curve is the training error of different hypothesis for our training sample. So this is ES8, and the other is the generalization error, which would be EH. Now, why is the minimum here non-zero?
Because the real one is not inside the fact.
Right, because we're talking about the unrealizable case, right? So we're not at liberty to assume that this is zero. The training error might or might not be zero, depending on the sample that you actually, the larger the sample, what do you assume will happen when you get larger samples? What will happen to the training error?
Closer to...
Right, so exactly. This curve will get closer to ES, will get closer to EP, and therefore the minimum training error is probably going to be non-zero, right? Because the curve is just going to be closer to it. Okay, so our interest now is to analyze the difference between these curves, basically to say when we see the training curve, what can we say about the generalization curve? Okay, it's sort of magic, right? Because we see something based on finite data, and you get to say something about this curve that you don't know. Okay, so let's get some bounds on this and see what interesting results we can deduce from that. Let's start. Okay, so I want to talk about the difference between training and generalization error. So ESH minus EPH. This is the difference between these curves. We'll look at the absolute value because we don't care about directions. And we want to look at the maximum discrepancy or maximum deviation between these two curves. Okay? So absolute difference, and we're maximizing. So we're looking for the age on this axis where the difference is larger. Okay? This is just a way to quantify the difference between these two curves. So generally, of course, this depends on the sample that you have, right? So we'll be interested in making probabilistic statements such as the probability that this difference between these curves is large, that probability is small, okay? So it's like the things we've been doing so far. So we want to look at the probability that we'll draw a sample from P such that this thing, say, is greater than epsilon. Okay? All right? Okay, so this is the thing that I want to analyze. This equals, I'm just going to rewrite it a little differently. This equals the probability. So when we say that the maximum is greater than epsilon, what does it mean? It means that one of the hypotheses in the hypothesis class is what? For one of the ages, this is greater than epsilon, right? There exists an age. That's a different way of saying it. Or the other way is that the union of this event is the union of events such that ESH minus EPH is greater than epsilon. Okay, so let's rewrite it this way. Is the union over age that of the event ESH minus EPH is greater than epsilon. Right? Why is it that? Because it's either this event is the event that this is true for the first age, or this is true for the second age, etc. Right? It has to happen for one of the ages. So these two things are the same. We did it before. Okay, so now this is suggestive as to what I want to do next. What do I want to do? When you see a union,
Bound in the.
right, I want to use the union bound. Okay? So this is the probability of a union of events. Okay? So I'm going to upper bound it by the sum of the probabilities of the events. Okay? The idea is that we want to simplify, we want to analyze this thing. Analyzing this event, the union, is hard, and analyzing each event for a particular age is much simpler as our unit. Okay? So we'll just write it as the sum over age in age, the probability of a sample such that ESH minus EPH is greater than absolute. Okay? So now the advantage is that within this sum, this is an event for a particular hypothesis. Okay? So this acts for a particular hypothesis age. Okay? Let's say in the rectangle example, this is for a particular rectangle. Right? So let's say this is the rectangle age. Okay? And I'm asking, for that particular rectangle, what is the probability that I'll draw a sample such that its training error is significantly different than from its generalization error. Okay? Right. So just to give us a picture of what's going on, so let's say this is the age. Okay, so now we're focusing on this particular rectangle. Forget about all other rectangles in the world, right? And there is the, let's say, the true rectangle, which is, let's say this is the true rectangle corresponding to P, okay? So when you see samples, they are generated from this, right? So we're asking, okay, what's the probability that this thing happens? Okay, so what can I use to bound this? What do you think?
Probability to get a sample
Mm-hmm.
in the area that it in.
So it's a probability to get a sample such that if I label it according to the black rectangle, okay, the number of errors that I get is significantly different from this, right? From if I label it using from this area here. So EPH is just this, right? Okay, but actually the drawing is, I mean, it's true, but it'll be confusing for you because I want to argue something formal to understand it. So what is, okay, let me argue this. I want to define a new variable, random variable vi, which is the following. It's the 0, 1 variable, so this is 0, 1, such that it looks at whether age, for that particular age, of xi is not equal to yi. Okay? So xi and yi are random variables, right? There's the x and the y that you see in the sample. And vi is the 0, 1 number that tells you if age is correct or incorrect on this sample. Okay. So what is ESH? It is just 1 over n, sum over I, vi. Correct? The empirical error is just this thing, right? It's the sum over all sample points. And for each sample point, you check whether age is correct or incorrect. Right? This is just the definition. Okay? All right. Now, what is EPH? What is it?
All the.
Well, EPH is just the expected value of Z1, which is the expected value of Z2, because there are IID, they are ID, right? So it's just our expected value of Z1. Okay? What's the generalization error? It's the probability when I draw points from P, right? That this will happen. That I will get an error. This is unclear to you? Okay. Do you get this? Okay. What is VPH? You remember? It's the probability that what? Exactly this, right? It's a probability when I sample X and Y according to P, that age of X will be different from Y. Correct? This is the generalization error, right? Of age. It's the probability when I draw points from P, that age will classify them wrong. Okay? So this is the probability of this event. It's because it's a 0, 1 number. It's exactly the same as the expected value of, let's say, the indicator of hx not equal. Right? Okay? The probability that this will happen is the same as saying 0 or 1, whether it happens or not, and taking the expected value.
The X and Y stand for a single point, right?
Yeah, so here, since I'm talking about generalization, there's no sample. I'm just drawing X, Y from P, okay, and repeating that. Okay, so basically, I mean, intuitively, it should make sense to you, right? This just measures the error of X, of the XY pair on age, okay? The empirical error is just the average of that, and the generalization error is the expected value of that. Okay? So I'm being very suggestive here. So I'm saying there is a Bernoulli variable VI, okay? It has an expected value EPH, right? And the empirical error is its empirical average. So what am I looking at here? This is the probability that a Bernoulli variable, for a Bernoulli variable with expected value EPH, its empirical average will be greater than epsilon different from its expected value. Okay? So what do you know that I can use here?
Inequality.
Right? Hofding.
Yeah.
Hofding inequality. Okay? So again, this is the probability that for a Bernoulli, for IID and IID Bernoulli variables, the average is different by more than epsilon from the expected value. And exactly, we have the Hofding inequality to bound that. So the Hofding inequality tells us that this is less than or equal. So I'll keep this. So I'm going to do Hofding for each one of these. So Hofding tells us that this is less than or equal to 2e minus 2n epsilon squared. Okay? Now note, this is the beauty of this. Right? Note that here, age is gone. Right? There is no dependence on the hypothesis. Okay? Because it's the same bound for all hypotheses. Because this thing is relative, okay? It doesn't really care about what age is itself. It cares about the discrepancy between training and generalization error for that particular age, right? And the bound is independent of the particular age, okay? Because it's only about discrepancy. And now, because we have a finite hypothesis class, we can just do this. Okay? And we got something very nice. We got that this thing, which supposedly depends on P, that we don't know, we got to upper bound it with something that does not depend on P. Right? So most cool learning bounds have this form. Okay? On the left-hand side, you have something that you don't know, this P, and on the right-hand side, it disappears. So this is sort of the main technical thing that we need to show. And now we can start having fun with the conclusions that we can draw from this. Okay? So basically, what does this say? It says if you use n samples, okay, for any epsilon, the probability that you will be that the difference between these curves will be greater than epsilon is at most this thing. Okay? So let's look at the order of magnitude here. What happens if you get more samples? What happens to the probability? It decreases, right? Makes sense. Okay? You should always look at these things to see that they're sensible. What happens when you make epsilon smaller? What happens to this? increases, right? Why?
For the part hard to.
Right, it's harder, right? It's harder to make the curves closer. What happens when you increase the hypothesis space? Right, it's harder to make, so this is maybe the key, the most interesting thing here, that it's harder to guarantee that the curves are close, if you have a large hypothesis. Okay? So this is what you pay for having, for picking among many hypotheses. Okay? You pay in uncertainty, if you want. Okay? Then that your training error that you see, that you might be happy with, because your hypothesis space is large, you are not allowed to deduce with high certainty that it's close to the generalization level. Okay? Good. Okay, so let's get some more implications from this. So let's say you see the training error, okay? And you want to tell me what you see ESH for a particular age, and you want to tell me what EPH is, okay? You've used n samples, okay? And you see ESH, and you want to say what EPH is. Okay? In other words, you want a confidence interval for EPH. Okay? This doesn't directly tell you how to do this, right? Okay? So we need to somehow figure out if we are using n samples, we want to bound the difference between these two things, but what do we need more to talk about confidence interval? A confidence, right? A delta, or an alpha, did we call it alpha? Okay. I think when we talked about confidence intervals, maybe we called it, never mind. We'll call it delta now. Okay. So, so things we deduce from this. So, we can get a 1 minus delta confidence interval on EPH using ESH. Okay, so basically we want, since we want a confidence of 1 minus delta, we want this thing to be what? Less than? We want this, the confidence here, to be less than delta, right? Okay? I'm saying I'm using n samples. I want to obtain a confidence interval of, with confidence 1 minus delta. So it means I want to find an epsilon here, okay, the width of the interval, such that I'll have confidence, what? So here, this will be less than delta. Okay? So let's do this. So we want, essentially, well, let's call all of this thing 1. So we want an epsilon such that 1, all this probability here, is less than delta, right? So we want to find an epsilon such that if we plug it in here, all of this probability will be less than delta, right? That's what the confidence interval means. Okay, so let's just do that. So let's write 2h e minus 2n epsilon squared. Is that what I have? Yeah. Is less than delta. So we can conclude from this that let's check the answer. We have that epsilon is greater than ln 2h over delta and 1 over 2n. Okay, just some algebra. Okay, so this says if you want this thing to be less than delta, that will be true as long as epsilon is greater than this thing. Okay? Is that fine? A lot of questions in the audience, so let's is it okay why I want this? I want to find an epsilon such that probability that I am more than epsilon away will be less than delta. Okay? What?
Epsilon square, right?
Here?
Right.
Yeah. So I did. Oh, there should be a square root somewhere. Sorry. Good, good. Very alert. Okay. Is that fine? Okay. Right. So this is just algebra now done correctly. And this basically tells you as long as you pick epsilon to be this thing or more, you'll get this confidence of right? Okay. So then the 1 minus delta confidence interval is essentially ESH minus this thing and 2 ESH plus this. Okay? So what we have deduced is that if this is your empirical error, your generalization error is guaranteed to be in this interval. Okay? With, of course, confidence greater than 100%. Okay? So that's again where I see that everything makes sense. As you get more training points, what happens?
The interval gets smaller.
Right, makes sense, right? So they get closer, these two things. As you get hypothesis class grows, interval grows, okay? So again, you're playing with uncertainty, okay? Basically. And as delta becomes smaller, so you're requiring more confidence, what happens?
So the interval
You pay, okay? So just make sure we do things that you pay correctly. Okay.
Yeah.
Yep.
Can you explain again shortly, please, why when the hypothesis space gets larger, we pay a price for generalization?
Mm-hmm. Because technically, I mean, you pay a price for requiring a confidence interval. Okay. If you want to say something concrete about the generalization error, using the training error, okay, because I mean intuitively, because if the sample space is, if the hypothesis space is large and you want to guarantee something across all the hypotheses, okay, so we want to make sure that something happens for all these things jointly, okay, because of this, okay. Then because you require something so strong, then you have to pay, okay, right, okay. Okay. So this is one nice thing that we get. What's the other? So the other is this theorem that I mentioned at the end of last class. So the other says, okay, let's say we take this training error, okay, and minimize it. Okay. So the minimizer is what do we call it? The ARM hypothesis, okay? So we minimize this, and we get the ARM hypothesis, okay? And what we're interested in is this thing, right? It's the generalization error of the ARM hypothesis, okay? This is your actual performance, right? Is that okay? Okay.
But this is a realizable case? How can you
Unrealizable.
So how can you know it's
Training error might be zero.
But it doesn't have to be zero.
Doesn't have to be. Okay? Okay. Let me I said in the beginning of class. Just to avoid confusion, let's do it. It can be, but it doesn't have to be. All right. Okay? So right? Oh, sorry, the pointer's moved now. So it's here. This is the generalization. Sorry?
Sorry for getting you in
No, that's
trouble.
fine. Let's move the minimum here away. I don't like that. Okay. So this is what we get. This is the best that we can get, right? This is the minimum generalization error for the true curve. Okay. So this thing we call the E star T. Okay. And we're interested in bounding the difference between these two, right? Because we want to know if we use the RM, how close are we to the best possible? So the theorem that I mentioned at the end of last class says that for every epsilon and delta greater than 0, if you take a number of samples that is greater than 2 over epsilon squared ln 2 h over delta, then for all p, that is regardless of what the true distribution is, it holds that you are essentially epsilon far from the best error you can get. So the generalization of ERM minus the best generalization error, E star P. The probability that this is greater than epsilon is smaller than this. Okay? Why do I not have absolute value here? Right, because these two things are on the same curve, they are on the EP curve, right? And E star P is the minimum of that curve. So this is going to be non-negative, right? If you see it here. Okay, E star P is the minimum, EP is something else, but it's not the minimum, so the difference is non-negative. Okay, good. So let me show that. So this basically says it's like a PAC, what we call a PAC type bound, tells you how many samples you need in order to guarantee certain accuracy with a certain probability or confidence. Okay? It basically tells you that if you take enough samples, this being enough, then you can guarantee this epsilon delta result. Okay, so let's do that. So proof. So it relies on this lemma that I mentioned last time, which Roy still owes you. So let's start from the left-hand side. Probability is generalization error of ERM minus P star P. The probability is greater than epsilon. Okay. So now I'm going to use this lemma. You remember the lemma? The lemma related this thing to what? Right, to the supremum. The lemma was not probabilistic at all, right? It just said that this difference here is less than twice the supremum of the difference between these curves. Okay? Would have written it. Want me to write it? Okay, let's write it. Okay, so the lemma, just to refresh our memory, says that the probability of generalization error of ERM minus best generalization error is less than twice supremum over H of the difference between the curves. Okay? So again, you can sort of imagine it's true. It's easy to show that if these curves are close, this measuring how close they are, then they're, if you minimize one, minimizing one, which is this thing, right? This is the minimum of the empirical error. Okay, if you minimize one, it'll be close to the minimum of the other. Right? Okay, essentially this. So if the curves are close, imagine the curves were really close. Right. Okay, this is not close. This is one, and this is the other. So if the curves are not allowed to diverge from each other too much, then if I minimize one and I look at the value on the other, it's going to be pretty close. Okay, that's the idea. And it's like two inequalities to show. Leave that for the exercise. Okay, good. So this is the lemma. And now it relates this thing that we're interested in to this difference between these curves. So the probability that this is greater than epsilon is essentially since this difference is less than this measure, okay? So what happens if I replace this with this? So I'm looking at something that is greater, right? So what happens to the probability?
It increases.
It increases, right? So let's see this again. So the probability, if I, instead of yeah, if, okay, yeah, so this is a random variable, okay? I'm asking what's the probability this random variable is greater than epsilon, okay? And now instead of this random variable, I'm taking a random variable that is greater, okay? So the event that is greater than epsilon is larger than the event that the original one is greater than, right? Okay? All right. So this would be less than the probability of that thing in there. So twice sup over H.
It's larger, no?
No, I'm putting a larger a random variable that is larger here. Okay. So the probability that this larger random variable is greater than something is greater, right? if that, okay, let's take an extreme example, always helpful. Let's say I'm taking a random variable that is always infinity, okay?
Okay.
What's the probability that's greater than epsilon?
One.
1, right? Okay? So it's greater than this,
Mm-hmm.
okay?
Yeah. So it's in the fall it should be the other way around, no?
No, no. So this is the infinity. This is the infinity, right?
Oh, right.
It's
I'm
because
tired.
it's not. It's fine. Okay. No, it is confusing. So we have this less than epsilon. Okay. And now I'm just going to move this to here. Okay. And now we've moved to something we know, right? This difference between the curves is something that we analyzed a few minutes ago. Okay. So, by the way, results like we had before that look at the difference between these two curves are called uniform convergence results, okay? Because they talk about the convergence of the empirical error to the generalization error across all ages, okay? That's why it's uniform. And it's something pretty fundamental in learning theory. You see these bounds all over the place. Okay, so this thing I already have from our previous analysis. The probability. Oh, sorry. Greater than epsilon. Okay, and this probability we have from a few minutes ago. We just had epsilon there, so I'll replace epsilon with epsilon over 2, and I will get. So this is from the previous result. This will be 2h e. So there we had e minus n epsilon squared, right? But now our epsilon is epsilon over 2. So we have 2n epsilon squared over 4. So we get n epsilon squared over 2. Okay? All right. So this we know this. And what do we want for this thing? What do we want for this left-hand side? We want it to be less than delta, right? Okay? So we want this thing to be less than delta. That is what we want. Okay? So if we just do algebra now, we get that n is great. We get the result, hopefully. The n is greater than 2 over epsilon squared ln 2h over 2. Okay? And that's what we want to do. Okay, good. That concludes that. Okay, so the third thing that we might be interested in, looking at, so there are three things here, right? There's epsilon, delta, and n. And the various results that I'm giving are sort of saying, okay, if you fix epsilon and delta, what do you have to set n to? Okay, and before when we talked about confidence intervals, I basically said if you fix n and delta, what is epsilon? Okay, and we can play these various games. It depends on what you're interested in. Okay, so now let's play a different game where we fix n and delta, and we ask how far, if you know EP, well, basically the confidence interval game. So if you fix n and delta, how far is EP, the generalization of ERM from E star? Okay, so we're just doing this inversion that we had before. So in 3, we'll say we'll fix n and fix confidence interval 1 minus delta confidence interval on what?
The best.
Well, on E star P, essentially, right? Okay, so
So we're playing with the epsilon.
right, so we're playing with epsilon, okay? So we just want to know if you learn, I mean, this is a common thing, right? You say, I'm going to learn with n samples, okay? And I want to know something about the best generalization, okay?
But it's going to be one-sided. No?
Right, it will be. So what do we want? We basically say, okay, we want this thing here, which 2 to prevent misunderstanding. So we want 2 to be less than delta, same as we had before. Okay, this is basically this, right? But now we assume that n is fixed, and we want to get epsilon, okay? Right? So this is 2 is less than delta, and now I just want to do the game where I get epsilon. So if I do that, I will get where is that? I get that epsilon is greater than square root 2 over n ln 2h over delta. And from this we conclude that the empirical error HF VRM, the generalization error VRM is less than or equal to E star P plus probably, I'm sorry, I want to do it the other way. So it's wrong in the notes. So E star P will be less than the empirical error of VRM plus this one. Okay?
Plus minus?
Let's see. I want this to be greater than epsilon. So this is plus. Right. No. I got this wrong. So it should be. Is it minus?
No,
Yeah, it is.
because you want it to be as smaller as possible, but you can't just make it smaller than the sample error.
What did I do
You have to
wrong?
take the sample error and add the epsilon.
No, but it must be smaller. No.
It must be smaller than
Okay.
the estimated error plus the epsilon to make a point.
What's wrong here? No. Okay. So let me write it differently. Okay. No, let's write it this way. So we get that the generalization error of VRM, which is something that we don't know, right? Okay, is greater than equal than E star P plus. Actually, it's not as useful as I want it to be. So square 2n ln 2h over delta. Yes. Oh no. Okay, sorry. So I guess that this is less than that. Okay. Because this is what we don't want, right? This is the wrong side of the inequality. Okay. Okay. Let me repeat. Okay. So this is the result that we get. Okay. Because the thing that is that happens with probability 1 minus delta is that this is less than epsilon, right? So I write less than epsilon here, and then I get this. And what this tells us is that if you use VRM, the generalization error of what you get, okay, is roughly, or is upper bounded by the best generalization that you can get, possibly in the class, plus some penalty, okay? Okay, so again, if you use VRM, what you can say about the generalization of VRM is that it's at most the best that you can get, E star P, okay, plus this thing. So when you use a larger hypothesis class, what happens? What you can say about the best DRM is you have to pay a penalty for the fact that you use the larger hypothesis class, okay, which makes sense. Okay, so it says the generalization error that you get again when you use DRM is what you can say about it is that it's it's the best that you can get in the class plus some penalty if you want. Where the penalty grows, the larger your hypothesis class.
Can I ask?
Okay? Yeah, sure.
Okay, so again, again, I don't understand why the larger the hypothesis class, you have to pay a price. If the hypothesis class is larger, then you have much more possibilities to pinpoint the
Right.
exact
But the difference between the curves, okay, it's generally harder to bound. Okay, if you want to, I mean, to bound the difference between these two things, the curves have to be close. If the curves are far, okay, then these two things might also be far, right? So it's great to minimize the training error, but the training error is not the thing that you want to minimize, okay? And the training curve, when you have a larger hypothesis class, it's harder to bound the difference between the curves, okay? Because you have to bound it across all possible hypotheses. Okay, so the bad thing that might happen to you is because you have many possible hypotheses, is that by chance one of them appears very good in terms of training error. Okay, but since the curves are different, okay, because it's hard to bound uniformly across all the curves, this is what you pay for trying to bound across the curve. Okay, then you might necessarily say. So essentially, this was wrong. What I meant to say is that the confidence interval is on the generalization error here. That's the confusion. Yep.
Didn't we have a confidence interval on that in relation to the...
No, you had a confidence interval for a particular age, not for ERM. So ERM, this thing here, is a random variable in itself. Okay? What we had before was, if you ask for a particular age, okay, give me a hypothesis, age, and I'll tell you how far it is from P. Okay? But this is more complicated because this says you saw the sample, you looked at the training curve, you minimized it, and you got this thing. So this thing is a random variable on its own. Okay?
But you can still minimize that with regard to at least the sample error.
What does that mean?
Right?
What would that mean? This thing is you looked at the sample,
and that gives us a certain error on our sample, minimum, right? So then we already have a bound on the generalization error, how far that can be from our sample error.
Right. But that bound only tells you, I mean, the bound on the generalization error says it's the training error plus something that is constant here, right? So anyway, you'd end up, if you want to minimize that bound, you would still end up minimizing the training error. Because the bound we had just a few minutes ago said that the generalization, that the difference, essentially that this curve is this curve plus some constant, right? So if you want to minimize this curve, that's what the ERM tells you. You'd better minimize this curve, right? They are far, but they are sort of uniformly far. Okay? But again, it's important to stress that ERM, okay, AJS ERM, all this thing is a random variable. Okay? It's a random variable where you take the sample, you look at the training error curve, and you choose the minimum. Okay? And because you do this greedy, it's a greedy thing, right? Because you try to minimize the training error. And because you do that, if you want to say something about the generalization error, you pay a price because you've minimized over a lot of things. Okay? So I want to focus on this again. So what this tells you, if you use ERM, what can you say about your generalization error? It has two components. Okay? One component is E star P. It's the best that you can do within your class. Okay? So if you have a very descriptive class, or a very large class, if you want, what happens to E star P? What happens to it?
Gets smaller.
Right. Okay? Okay.
Wait, E star P gets smaller?
Yeah.
But isn't that totally unrelated to the hypothesis class?
No. E star P is the error of the best hypothesis in your class. Okay? So if you now take a larger class, okay?
Yeah.
So let's say you have two hypothesis classes where H1 is a subset of H2. Okay?
Yeah.
So E star P for H1 will be what? That E star P for H2 will be great. Okay? It's essentially just you increase the axis here, right? So this is, let's say, H1. Oops. And let's say it looks like this. Okay? EPA. And now I add H2. Okay? Let's say this is H2. Oh, my edges are terrible today. Sorry. So let's say it looks something like this. Okay? It can't get any worse, right? You've added more stuff. So the minimum here, this is E star P for H1, and this is E star P for H2. Okay? I mean, you've just made things more, you've allowed more options, right? So the best you can do is better. That's sort of makes sense. Okay, but what happens to the other term? This term. Okay, so if we look at square root 2 over n ln 2, doesn't matter all these things really, size of h1, and square root 2 over n ln 2 size of h2 over delta. What happens here? So h1 is smaller, right? So this is smaller. Okay? Right? Yep.
But the fact that the size of H1 and the size of H2 appear here is just the consequence of that we use the union bound, right? The union bound gave
Right.
us this
So
term.
you're saying maybe I could do a better analysis?
If we have a better, if we consider the overlap between the different hypotheses, we don't need to use the union bound anymore.
Excellent
We
point.
could be much better.
Excellent point. But the answer is that it's actually it is, in terms of order of magnitude, it's the best bound you can get. So it's also a lower bound.
And is that also true for the Höfting inequality?
No, it doesn't mean that that bound in itself is tight, but this analysis where we say where we get this dependence on the sample, the size of the hypothesis class, is tight. So we get this not because our math is crappy, but because it's the best that can be done. So in the exercise, you'll actually show a lower bound. It's a very good question that you asked.
So say if all the hypotheses, if the events related to these hypotheses all completely coincide, then instead of
Right.
the size of
No,
the
so
one,
generally
there's
there
one
would be,
there.
you could construct cases like that, but the worst case, so there will be cases where this is real, okay?
When there is no overlap at all between the different hypotheses.
Yeah, for example. Okay. Okay. But in terms of the intuition, this basically tells you all the story of learning theory. Okay? The trade-off here is the inherent trade-off that you should think of. So your generalization error when you learn with the hypothesis class has two components. One is the best that you can do within this class. Okay? And this, as you use a larger hypothesis class, this decreases. So in this sense, it's better to use larger classes. But what happens? You pay a penalty. If you use a larger class, because you've optimized over more things, you pay this penalty. Okay? So this is often known as the complexity trade. Okay? So what ideally should you do?
Increase them.
So given this trade-off,
We need to see the minimum of or the maximum of this.
well, you would want to get the minimum of this, right? So if you have multiple hypothesis classes to choose from, you would want the one that minimizes this, right?
They're involved.
Right, the sum. Exactly. So, but what's the problem? You don't know this guy, right? P. This is the only thing that this one you can have, right? This one you can't. What does this depend on? The true rule, right? So what's the story here really? There is this true rule here, this P, okay? And there is your hypothesis class. Let's say this is H1. Okay? So we are unrealizable that so P lies outside this class. Okay? Now, so how do we, so if we want to get to P, it makes sense to use a larger class, right? Okay? So now P is in this class. So if star P went to what? 0. But we paid this term. Okay? So there's a trade-off. So what's the best thing that could happen really? If we had, okay, let's say this is P. So wouldn't it be lovely if we had this H3 that looks like this? Okay? So best thing in life is to use the right set of rules and not to have too many rules. Okay? So it's the same as with the bias variance trade-off that we talked about. Okay? This is also sometimes referred to as the bias variance. Okay? So this is basically, in terms of intuition, this is what you need to know about learning theory. You need the right set of rules, and it better be small. And this is the theory. All this theory that we've done basically tells you it's quantifies these measures. Okay, good. So we're done with that, and in the next hour we'll talk about the case of infinite hypothesis. Okay.
Vänta.
אני אומר, נגיד שאנחנו רוצים לחשוב האם להשתמש בכותב המחלקת כותב אבטחה, או שנייה, שאחת היא יותר גדולה מהשנייה, ומכילה אותה, בסדר? אז אני אומר, אז לכאורה הגוף הדיזיבל הזה אומר לה, מה תהיה שגיאת ההכללה שלה? אם אתה משתמש בזה אין דוגמאות, מה תהיה שגיאת ההכללה שלה בכל אחד מהמקרים? נכון, מה ההבדל במקרים? רק הגודל הזה והאיסטרפיס. איסטרפיס זה אומר הכי טוב בתוך המחלקה. הוא חייב להיות. אם יש לך הכלה, כן, אתה צודק, אם הוא סתם יותר גדול זה לא אומר, אוקיי? אבל אם המוכלים זה הכלה, כן.
אוקיי, אז ברגע שאנחנו לא יודעים הבנתי. תודה.
כשאתה עובר לאינסופי, אתה יכול קודם לדבר מתי הגיוני שיהיה סופי.
מתי הגיוני שיהיה סופי? ואם אתם מחשבים,
if you have finite states,
if you have finite decisions.
so then it is always finite, so it's always actually finite.
So Shai calls this the thinking tree. He says you do perceptron, okay, with steady-state computer, and you have 22 possible hypotheses. Essentially, we don't really need infinite, but the theory is interesting because it's telling.
Right, that point these sounds probably
They become, right, because they are totally dependent on the resolution. Before bit in the order before. But if you actually look at the real, the structure of the I mean, the analysis that we do for infinite also applies to time. Just a different way. It's a way of quantifying a hypothesis class size that is not, or complexity that is not
יכול להיות שיש דרך.
ברגע שיש לנו את הפונקציה MDT, זה
לגבי
בעיה של פונקציה.
what I have is a situation where I want to validate that things come from the same distribution, or so sometimes I want to, I don't know if it's good enough to just not reject.
ברגע שהדבר הזה לא קורה,
actually I think if this is what you want, then it makes sense. Same non-hypothesis. The question is, do I have enough evidence to say that this is?
זה מגדיל את זה.
But I don't know if I'll tell you a little bit more what's going on is a kind of a growing neuron morphology. Where I see a few morphologies, and now I use an algorithm to grow new artificial morphologies. And now I want to validate what I grew legitimate. So I feel like I want stronger. What I would want is to rule out that
You want to argue that they're the same or that
I want to argue that
they're the same?
זה משהו קטן, חכה משהו קטן, גם הוא יותר גדול מזה, הוא עדיין קטן אחד.
הדבר הזה פשוט זה הסתברות של פי של
it's raised by one, like null hypothesis to be the difference.
Yeah.
But there's no.
ההסתברות הזאת.
Right.
ההסתברות של F I בהינתן תטא I, תטא T.
לא, כל זה ביחד. לא, זה כן, זה.
לא, כאילו ההסתברות למטה זה זה. זה הסתברות למטה. כאילו בייס, לפי בייס.
נכון, יש לי את זה גם כן. XI, סבבה.
זה הסתברות, לא הסתברות, זה קטן מאחד.
נכון, בסדר.
לא, האמת שזה לא קטן.
קטן שווה.
זה לא קטן.
זה קטן שווה.
לא, אבל לא חלק שזה לא מאחד. שמעת איך עכשיו פה?
נכון, זה לא נכון.
Well, you can say that you don't reject, right?
אבל
You say with
הדבר
with
הזה,
No, you can say I saw that according to the data I cannot reject the
כאילו כן זה
It does speak to what you want to show, right?
יודע שדבר הזה פרופורציוני, אבל בסופו של דבר הדרך הנכונה להגיע לדבר הזה זה לחשב את זה.
תראה, ההוכחה תהיה פתאום יעבור סבבה.
Because, I mean, essentially what you can say is, let's say you know the true distribution, okay?
כל שאומרים תעשו את זה.
ונתן טקסט? איפה זה כתוב?
בסוף התרגיל.
And again, it's more natural to reject than
לא, אבל... יש לי פה, איפה כתוב? אולי כאן? כן, רגע. אוקיי.
זה גם הגיוני, כי את לא יודעת את זה, את לא יכולה...
כן, אז יש לי כאן תרגום.
yeah, it's almost meaningless to ascertain that they're the same, right?
זה הנתינת החיסון אוקיי,
there is probably a better answer.
אפשר גם ככה.
היה לך שיעור כזה?
לא.
I think they usually the tests are. So we looked at these cases. It's really cute.
Yeah.
וואי, זה כאילו זה גם היה סך הכל גם אין שלי.
Yeah.
זה גם ממש כזה. זה כאילו היה סך הכל גם
Yeah, to just say, okay, I don't reject. Because especially if I'm generating.
Yeah.
I don't reject it.
I don't have enough. Yeah, it says I don't have enough evidence to say that they are not.
So like what?
No, because it says no. In other words, it does say the probability of seeing this type of observation under so H, the p-value on Earth is always conditional on H. Okay, so this says probability of seeing these observations given that they are the same is pretty high. It's something. Okay, so you could just use that number, right? You could say, okay, this is the probability of seeing
Sort of a high.
well, you have the number, right? You say it's 90% chance of seeing something like okay.
הכי טוב זה להבין כמה שאתה
So it's like a high p-value.
Yeah, low, high p-value.
A high p-value.
No, p-value should be small to begin with. Okay? No, it's true. If you see a high p-value, it says that you're it's tricky. It says if you see a high p-value, it says that the observation is very consistent with your
So in terms of saying what's good enough, though, right? You know, when you're rejecting, you say smaller than 0.05.
right. I won't reject because the tail
And then I will say
אבל אם העולם...
say okay, I'm not gonna reject.
yeah, I think, but then the null it's much harder with if you say that the nullities are different, but you don't quantify how different they are, then they could be arbitrarily epsilon away, and then still you won't be able to.
כן, רק קודם כל, לא
Yeah, I don't, and because I don't have a parameter, I can't quantify how different, say, at least is different.
אוקיי, נכון. את
Yeah,
מגיעה לזה.
if you had two distinct candidates, that would be much easier. Then you could do two sides. Then the two types of like you could even do something simpler where you say, okay, when I see the sample and I want to predict whether it comes from you could do the classifier. Look at the sample and say it comes from this distribution and that. And if you have a classifier with high with low error, predict where it's coming from, that's also good. But if you don't have the alternative is not going to find. If you had two populations, that might actually make sense. You have like two populations in mind. That when you grow it, it actually looks a lot more.
לא, אז אני חיפשתי, ואז ראיתי שזה כאילו, מה שאנחנו יודעים על זה שהיא מתפלגת.
It's just
המקרי שהוא מבחן.
convincing argument.
או סטטיסטים של X.
Another thing of p-values is something that the community agrees on at some point. You could argue a lot about whether that makes sense or not. It's a social thing.
שהוא אחד במבחן, ואתה יכול ממנו ללמוד לכל היית.
So usually if you want to know what statistics you should do, you should look at other papers in the community.
כן.
See how what statistics they do as that type of statistics.
שאלה שצריכה להבין.
אבל איך ידעת שהוא מתפלג?
שאלתי שלא מתפלג. שאלה 2? לא ידעתי שהוא מתפלג.
אבל התאמצת בזה.
still,
אבל
רן, T של
לא,
X.
שלא צריך לדעת
לא,
באופן?
לא.
בדיוק
אוקיי,
זה
אז
אפילו
אני
אחד
אסביר.
התמיכה.
T של X זה מקרי.
נכון.
T של X זה לגמרי משנה מקרי, לא מפרק T, לא שום דבר.
כן, אם יש לך...
לא יודעת,
אם יש לך...
פשוט יכול לדעת, צריך לדעת מה...
אם יש לך X...
של חורות, אז כן. למרות שזה מה צריך.
2, בסדר? T של X זה יכול להיות למשל... זה משנה מקרי, סתם תעשי ממוצע. זה גם יכול להיות סכום שלהם, זה יכול להיות שור רשו של X. אז יש לזה התפלגות. זה שני מקרים. ולכן ככה זה שני מקרים.
All right, so we are moving to infinite hypothesis classes. Okay. Up to now, really, the complexity measure, or the only place where the hypothesis class came into our bounds was the size of the hypothesis class. So this was the measure of the complexity, if you want, of the class. And obviously, that's only meaningful if we have finite hypothesis classes. So Itamar asked me during the break a good question. Why should we talk about? Did you say why should we talk about infinite or finite?
Why should we talk about finite?
Okay, so I answered why should we talk about infinite? Okay, so I'm from a computer science department, and essentially in computers there is nothing is infinite. Okay, so even numbers, real numbers, we don't have real numbers. We represent numbers by bits, right? So the numbers that a computer can talk about are finite, right? Okay. If you have 32 bits, then you can sort of talk about 2 to the 32 possible numbers. Okay. So in a sense, when you discretize things, as we do with computers, with bits, we don't really have anything that's infinite. Okay. So for example, in our rectangle example, even if I were to do this game with a computer and I would represent the rectangle, then the corners, the coordinates of the corner and the length will all be represented with a finite number of bits, right? Okay, and therefore there's a finite number of possible rectangles that I can represent. Okay, so I'm actually in the finite. Supposedly I'm in the finite case. Okay, but now let's say I build a new computer with 64 bits. Okay, then I can represent these rectangles with more bits, right? So the size of my hypothesis class grows. But essentially, it seems sort of dumb, right? It's it would be dependent on the resolution. The main thing here is that we're talking about rectangles, and they have certain shapes and certain descriptive powers. So it makes sense. It seems more clean to just talk about the infinite case where I can reason about all possible rectangles. Okay? So I would say, in a sense, perhaps we do always use the finite hypothesis class, but even if we use the finite hypothesis class, it doesn't necessarily make sense to talk about the size or the number of different hypotheses, but we should look for something something that describes the complexity of the hypothesis class that is not necessarily its size. Okay? So basically what I want to do now is for a hypothesis class, whether it's finite or infinite, give a different complexity measure for the class that is not its size. Okay? You'll be able to use it also for finite classes, but it will also apply to the infinite. Okay. So basically, I want to, in the previous bounds we had this thing, the size of the hypothesis class, which measures the complexity of the class, and I want to replace this with something that also applies in the infinite case, and also looks more at the structure of the hypothesis. Okay. Right. So again, what I want is a measure of the quote-unquote complexity of the hypothesis class. Okay? Right. So we want a measure of the complexity, or if you want the descriptive power of a hypothesis class. So there are various ways of doing it. There are various measures that are relevant and provide bounds like we had before. We will focus on measure known as the VC dimension. So first, who has seen this somewhere?
VC.
Vatnik, Chervoninky. More familiar now? Okay. Anyway, so we will have this VC dimension is a number describing the complexity of the class. Okay, and it'll play the same role as the size of H. Okay.
Will you explain earlier what complexity or expressive power means, or should we understand it now?
No, you will understand. Okay, what it means intuitively is how much things can this class describe. Okay, how many rules can this class describe? Okay, so for example, in the finite case, if I take a class H1, okay, and now I take a larger class that contains it, H2, then H2 is more descriptive than H1, right? Because it can describe more rules. Okay. Okay.
But you can have two infinite number of two classes that are infinite. They can
Right.
have exactly the same number of.
Right. So size, when you move to infinite hypothesis classes, size becomes sort of irrelevant. Okay. So we want something that captures this notion of descriptive power. Okay. But it's not size. Size is just not. Is what?
No.
It's not. What's the word? Subtle. Okay. Especially when you do infinite, it becomes irrelevant. Okay.
It relates to the earlier question about like the overlap of hypotheses, kind of like you talk about you have a larger hypothesis class in terms of size, but it kind of doesn't add descriptive power.
Yeah, you could. Right. So generally, I would say that size is not the right. Because I could have even, let's take the dumbest example where I say I have essentially one hypothesis, but I multiply it 1,000,000 times. Okay. So I say, oh, it's 1,000,000. There's 1,000,000 hypotheses in here. Or it's the same, but it's like epsilon different. Okay. So right, size is just not. It's just not subtle. Okay.
Like the dimension of a vector space, because if it's infinite, but it has a dimension which.
Right. So it's okay. Very good. So we want. I mean, so you're right. Okay. So it's a measure like that. Okay. But it's non-trivial to define. I mean, it took Vapnik, I don't know, it took humanity until 1970 to come up with this thing, and because we want something that's. It doesn't just have to be a number. It has to be a number that tells us something about how we can learn in this class. Okay. Okay. So basically, what we're after is a number that, given a hypothesis class, will tell us how descriptive this class is. Okay? If it can describe many rules, it should have a high number. If it can describe a few rules, it should have a low number. Okay? Okay. So I will run you through this definition of VC dimension, which I think will make sense to you, and then I'll give some bounds. I won't prove those because it'll take us too long to prove, but I'll give you the results to get the intuition. Okay. So let's think of this class of say axis aligned rectangles. Okay. In some sense, it seems like a simple class, right? What does it mean that it's simple? Because the rules that it can define are fairly limited, right? It can only define the rule where all the pluses are inside the rectangle and all the minuses are outside. Okay. So, for example, it cannot describe, if I look at, say, this training sample cannot be described by a rectangle, right? So there are limits to what this thing can describe. Okay? Right. So how can we quantify these limits? Okay, the descriptive power. So, sorry?
Index.
Sorry? You said volume?
Volume?
No, I didn't say volume. What did you say?
Same volume.
I said index.
Index. Okay, but how?
For example, this has the size of the real number in the power of 2, right? The rectangle.
Okay, let's try. I mean, I would say my first guess would be if I had to quantify the complexity of rectangles, I would say it's 4, right? Why? Because there are 4 parameters, right?
Two.
Well, four parameters to specify a rectangle. Right, the corner is two numbers, and these are another two. Alright, okay? So intuitively you think this is what you get, and the VC dimension of rectangles is 4. You'll be glad to hear. Generally, there are some. Okay. So anyway, so let's try to quantify this first. So Bartek's idea was, how do you quantify the complexity of a hypothesis plan? You give it a set of points. Let's say I look at these 2 points, okay? And now I ask the hypothesis class, how can you label these points? Look at hypothesis in your class, okay? How can you label them? Can you label them both plus? Can you? You can, right? Just do this, okay? Okay. Can you label them? Can you do this? You can, right? Okay. So I could probably do all possible labels. How many possible labelings are there for 2 points? 4. So I can do all 4, right? Okay. So VC dimension is greater than 2. Okay. This is I'm giving you a story definition. We'll do it formally. Okay. How about 3? So any 3 points that I take, can I label them arbitrarily?
Yeah.
Yeah, I can. So I'll just do a picture. It's somewhat deceiving, the picture, but okay. So I can do this, right?
If you take the line,
Okay, but the question is, I'll give you a worse example. What if you take, so let's come back to 2 points, and I take 2 points that are on the same point, okay? So I can't label them, right?
One point.
Right.
So
So I can't do plus minus here, right?
The true label will say.
Sorry?
But there will be no true label.
I'm not talking about true label now. I'm just, the game is that I give you a bunch of points, and I ask you, in how many different ways can you label them, okay? Right? So, as you suggested, if I give you 2 points that are on the same at the same point, then in how many ways can I label them? 2. Okay. So, but it seems like an idiotic example, right? So the question would be, can I find a set of 2 points that I can label in all ways? Okay. All right. So let's say 3. 3.
So we just ignore those examples.
Yeah, because in a sense they don't capture really complexity, right? Because I mean, if you put all points on the same at the same place, then
Yeah, but
obviously.
on the line, as you said.
So on the line is the same thing, right? It's a specific case that you construct that is maybe hard to label in different ways. Okay, but I'm trying to capture. So the game I'm playing is I'm letting the hypothesis class try to demonstrate its power to me. Okay. Okay, so the hypothesis class tells me I can label 3 points in arbitrary ways. Okay. But not right. They exist. Right. Okay. So this is the game that we play. So 3 points. Let's say like this. I can label in arbitrary ways. Right. What about 4?
You said earlier we can.
So 4 I still can, right? I can put all of them inside. I can put these inside. I can put 3 inside, etc. Okay. What about 5?
No.
Okay. Let's look at 5.
One is inside the circle.
Okay. So 5. These are. I want to argue that this is a general setup of 5 points. Okay. So what happens to the 5th point? There's always a 5th point. That is what?
Inside the circle.
Well, it's inside in the sense that it's not the topmost, it's not the leftmost, it's not the rightmost, and it's not the bottommost, right? Okay?
It's more.
Yeah. Okay. It's actually not inside the convex Hardy band, because it could be here. Okay? Okay. So we should. Okay. But still, it's not the extreme on any dimension, right? It's like this Kaveret song. You know, she's not lo mucha mida, lo gvura mida, it's באמצע. Okay, so it's not extreme on any thing. So what can we say about this point? Can we do this labeling? Other way. Yeah, this one. Can we label it this way? No, right? Because if we want all these to be pluses, we have to build a rectangle like this, right? And now this one cannot be labeled.
Why can't you just build a rectangle within the 4 plus labels and?
It has to be parallel to the.
It has to be parallel.
Yeah, it's actually aligned rectangle. Okay, you're right. If I have another degree of freedom, then this is not the right dimension. Okay, so this is the game. Okay, so now we see that for 5 points, we We cannot label them arbitrarily. Okay? There are certain, yep.
But, I mean, if you have, for example, 3 points in a line,
Mm-hmm.
you can never label the two outer points as plus and
Right, so I
minus.
said, that's what we said before, that the game is that the class gets to choose the points, okay? So the hypothesis class tells you, I can label 4 points, there exists a set of 4 points that I can label in an arbitrary way, okay? So the class gets to choose the points.
And there's no set of 5 points that can be
No, because this is what I want to argue, this is a general setting of 5 points. So among 5 points, there will always be one that is neither the topmost, bottommost, okay? So if we play the game where the class gets to choose these 5 points, I'm arguing that the hypothesis class can never choose a set of 5 points that it can label arbitrary, okay? Okay? So we have to, all your questions are very good in the sense that we have to make sure that this is really a general setting for 5 points. And I haven't cheated somehow. It's very easy to get this wrong. Okay, so anyway, this is the idea. So the idea is that we measure the complexity of a hypothesis class by asking what is the largest set of points that the hypothesis class can label arbitrarily. Okay?
Can find
Right.
4 points that for them can.
Right. Okay. Let me do the quantifiers and we'll see. Okay, but this was just for intuition. Okay. So okay. So there'll be some definitions now. For a sample S, we find pi h s. So h is a hypothesis class to be the set of all labelings or labelings that h can assign to S. So, for example, if so by S I mean there are no the S is x1 to xn, so there are n points. Okay. So let's say S is these 2 points. Okay. So this is x1 and x2. Okay. So what would be pi h s? So I can label it as 1, 1. I can label it as minus 1, minus 1. I can label it as minus 1. Oh, I think I'm using 0, 1. I'm sorry. So I'll just use 0 and 1 for the classes. 0, 1, 1, 1, 1, 0, and 0, 1. Okay?
0, 0.
And 0, 0. Okay? So for this particular set of 2 points, the hypothesis class of rectangles can label it in all possible forwards. Okay? Okay. So again, pi hs is a number that given a sample, for every sample there is a number. Okay? So if I take x1 and x2 to be the same point, what is pi h of that? Well, it's either 0, 0 or 1, 1, right? Okay? I can either label them both as positive or both as negative. Is that okay? Okay. So this is for a particular sample, and there will be some samples that are maybe anomalous examples, and some samples that are maybe more general. Okay? So, as we said, we had this discussion a few times now. We'll be interested in the sample that has the largest number of labelings. These labelings are sometimes called dichotomies. Okay, you've seen
I'm so interested in the sample that has the lowest number of it bounds the number of possibilities that you can have.
Because this, you see, you can always do there will always be a sample where the number of labelings will be 2.
But
okay?
let's say a sample that is not, this is not, I think it's called general position. Like
Yeah,
something
right.
that is totally general, then find the minimal thing that can.
So you could have done that, but it's more natural to ask if you can play with the sample as much as you want, okay? And try to find a sample that gets the maximum number of labelings. The point is that this would break down like we had with the 5, okay? This would break down at some point. So it's easier to define this way. You could have thought of maybe trying to block anomalous samples, okay? But it's easier to define this.
In the rectangle case, can't I find any 5 points that can be labeled?
No.
Okay.
I argued why not? Because I said among 5 points, one will always not be extreme, okay? So if you want the other 4 points to be in the rectangle, that 5th point will have to be inside. Okay? So it works. You could try to block sort of anomalous examples, but it works this way. So you don't have to do that. Okay. So now I will define. So what I'm really interested in is not the labelings themselves, but their numbers, right? The number of different labelings. So what I'm interested in is let's call it pi h n, which is the maximum number of possible labels. So pi h s is the number of labels for a sample of s, and I want to maximize that over all possible samples of size n. Okay? So pi h n is the maximum number of labeling that you can assign to a sample of size n. Okay? Right? So what is pi h for our rectangle? What is pi h 1? 2, right? What is pi h 2? 4. What is pi h 3? 8, right? What is pi h 4? Okay, and punchline, what is pi h 5? What is it? Well, no, it's not necessarily 16, but it's not what?
Not 30.
Right, so it's strictly less than 30, okay?
You can't say that it is into the 16?
No, it's actually not 30.
Because the last extreme point, isn't it dependent on the decision to add the 4?
No. So you could do maybe I'll show some examples. 1, 2, 3, 4, 5. No, so you still have, when you decide on, it's not that when I, let's see, let's do it this way. So this is the 5th point. So I can do all of these as pluses, okay? But it doesn't decide on this one. Because I can do all of these pluses and this one is a plus. I can do all of these pluses and this one is a minus, right? So you wanted to say something like the labelings of 4 determines the 5th, but it's not true. Okay? Okay? Because I can do either this or this, right? So I have
No, but it looks like the middle one is dependent on the other 4.
no, it's not true. I mean,
The middle one
just
is true.
The middle one is true, but not for any of the others.
The other point.
yeah, okay. It's true for that one, but not for this one. Okay?
You can take only the 2 bottom ones or the 3 bottom ones.
You're right that if I have, the 5th one in the middle, if I label all these as pluses, this one has to be a plus. Okay? But if I label these 2 as pluses and this as minus, this one could be either plus or minus. Okay? So the answer is, and it's not trivial to see, is that this grows. It will not grow exponentially, but it will grow polynomially in n. Okay? This is okay. Well, we'll get there. Right, but okay. So we've seen this, and now we can define the VC dimension. So let's just give this a name. So this is called the growth function. Okay, and just another terminology. We don't need it, but it's often used. We say that if pi h s where s is of size n equals 2 to the n, we say that s is shattered. This is a nice term. Shattered by h. Okay? So if you have a sample of size n, okay, and h can label it in all different ways, okay? So if s number of labelings that H can apply to it is the all possible labels, we say that it shatters it. Like קורא לו את הצורה.
Keeps it.
Yeah, keeps it right.
But
But can't we just say that n is equal or smaller than 4 instead of...
What? This?
Yes.
Oh, this is just a definition. It's just a term. Okay.
Okay, but
Ignore it.
it's unnecessary.
Yeah, I just said I just like the term, so I thought mention it. Okay, so now we're ready for the definition of the VC dimension. So the VC dimension of a hypothesis class H is the largest n such that what? That pi hn equals 2 to the. Okay? So it's the largest sample for which you can still, it's essentially the largest sample that you can shatter, right? Or the largest sample for which you can apply all different labels. Okay?
The largest n for which a sample of size n
exists, that is shattered. Okay?
Can you say n is shattered, or you always say a sample is
No, I wouldn't say n is shattered.
You always say a sample.
Yeah. Well, maybe you could say.
that exists a sample of size n that is
Yeah, here I don't need to say exist because pi hn is already contains the existence, right? Pi hn is maximization over all possible s's of size n divided. Okay. All right. So.
Are you saying that the maximizing sample is always typical or in general position?
Yeah, I'm saying that it captures the general behavior. Okay.
Is that true for all sorts of groups?
No, you can probably build hypothesis classes where the VC is obtained by very strange access. It is a worst case analysis. Okay, I'll give you that. It's true. But in many cases, the general case does capture it, or the average case as well. Okay? Yep.
So if you define it with like excluding samples of probability 0 instead of the maximum case.
Of probability. Well, we don't want to consider. But we don't want to consider the probability over x at all. We want to give a result that's general. You're right that if my sample is obtained with x's that are very unlikely, then or unlikely at all, then the result is it's an overkill, right? But the results that we want are like that we had in the previous class. We want to be agnostic to the true distribution. Okay? So we are considering it's all worst case analysis in a sense, and this is some critique against this analysis. And there are a lot of works on analyzing particular distributions. Okay? So it's a good point. Okay. So this VC dimension is going to be our measure of complexity of the class. So I just want to link this back to the finite case and then show you some generalization results. So we'll just write VC div of H. Okay, I'll just denote it by VC div of H. So let's just give you one example, which is illustrated. Okay. So before I go into to examples of VC, I want to give you the generalization bounds. Okay. So this again is a measure of complexity of hypothesis test, and the point is to show that it's useful somehow in analyzing learning. Okay. So here's the main theorem that that allows us to talk about learnability with VC dimensions. So it says the following. It's a uniform convergence result. It says the probability of a sample such that the supremum over H in H of ESH minus EPH is greater than epsilon. So this is the stuff that we had before. Before we had here what? We had two sides of the hypothesis class, E minus blah, blah. Okay? So this will be replaced by 4 times pi H 2n E minus n epsilon squared over n. Okay? So this is the equivalent. This theorem is due to Vapnik somewhere in the 70s. And before we had here, we had 2H E minus, what was it, 2n E epsilon squared? Yes? Yeah. Okay? So we see that the results are similar, except this, the number of labeling replaces, okay? So it says, it makes a lot more sense, right? Well, there's 2n here, but let's ignore that. It says, really, the thing that you care about, the thing that measures H, is not how many H's there are, how many hypotheses there are, but the number of different labelings that the hypothesis can ascribe to a sample of size. Well, it's 2n, but again, ignore this 2, okay? All right? So now, if you have a finite VC dimension, what happens to pi H 2n? What can you say about it?
It's smaller than...
Right. Thus far, the only thing we can say about it is that it's not exponential. I mean, it's not 2 to the 2n, right? Okay.
The alpha? Then?
Yeah. Okay. So actually, thus far, this is not necessarily a very useful result, because it could be that pi H 2n is what? Well, it could be still exponential in n, but not 2 to the 2n, right? It could be 2 to the n. So now the critical thing is that this thing is actually polynomial in n. Okay? This is what makes this a useful result. So let me give you the other result here. So there's another theorem. And this one is due to well, Sauer and also Shelah from here. Yeah, it's called the Sauer theorem or Sauer-Shelah theorem. Sauer-Shelah, yeah. Right. And this says, well, it says something a bit different, but this is the result of interest to us, is that pi H n, okay, I should say this way, if H has VC dimension D, then pi H n, so the number of different labelings that a sample size n can have, is less than or equal to E n over D to the power of D. Okay? So this is somewhat surprising, very important, and not that trivial. It's not very hard to show, but it's not immediate. And what it says is that this number of different labelings, okay, is in n, its dependence on n is what? Polynomial, okay? Whereas if you're shattered, in the case that all labelings are possible, this is 2 to the n. What this says is that if your VC dimension is finite, then this holds. I need to add something. If for n greater than d, so this holds for n greater than d. Okay. So up to d, what happens? What is pi h n? It's 2 to the n, right? Okay, but after d, we have
before the dimension is 2 to the n.
Yeah, I think that's what it says. Up to.
Up to.
Yeah. Okay.
So this is E times n, or?
Yeah, E times E is 2 points. you can see the power of this theorem. Okay? So what this basically says is that if you have finite BC dimension, pi h2n is polynomial in n. Okay? And therefore all this thing is what in n?
Polynomial.
Exponential. Okay? Because the exponent decreases
Yeah.
much faster than the polynomial. Okay? So this thing, if you take n large enough, will go to 0. Okay? So the conclusion before we do it more technically is that because of this result, because of this the Sharp theorem, we know that if we choose n large enough, these two curves could be arbitrary groups. Okay? So this is the crux of the BC theorem. It's these two things together. This uniform convergence bound, which ties the difference between these curves to the growth function, and the fact that if you have finite BC dimension, the growth function is polynomial in n. Okay? Right.
So it solves the problem of having whether to have. I mean, what we did in the first theorem was it was the size. It was larger than something, which is 2 times the size of the h, like the size of h, multiplied by
Right. We have
exponential.
two h here, right? 2h
And
e minus 2n h to the square. So h, so it makes sense, right? If you have a finite hypothesis test, then the number of different labelings that you can assign is what? What is the most you can assign? It's just the number of hypotheses, right? So this clearly upper-bounds this in the finite case. Okay? So now we're sort of, once we have this and this, we're we can plug this in here, and we're more or less at the state we were when we talked about the finite case. We have these bounds, and now we can use those to deduce all the things that we deduced before. So I'm not going to do all the derivations. It's pretty similar, so I'll just give you a bunch of results.
but we are not dependent on the size of the
Of what?
of the h, right?
Well, you are
If
dependent.
we
The bound is dependent only on the VC dimension. Okay. So the VC dimension replaces the size of it.
So now we can calculate what h we want,
Well, for a particular hypothesis class, you can calculate the VC dimension. Okay. And it will come up. I'll show you the bounds, and you'll see what comes up. Okay. So now what I want to do, I won't do the math. I'll just give you the result. Is to take this uniform convergence result and draw the conclusions that I did in the finite case, and we'll get something pretty similar. Okay. So one is confidence interval on EPH. So we get that EPH is less than ESH plus. So before we had something like square root 2 over n log size of h, right? So now we'll have 8 over n. Ignore the constants; they're not really important. D ln 2en over d plus ln 4 over delta. Okay, where d is the VC dimension. ESH minus that thing. Okay.
What is the line on what?
Ln 2en. Yeah, sorry. Okay. So in terms of order of magnitude, this is d over n. Okay. The ln is that's important here. So again, as d gets larger, okay, we have a larger confidence interval. Okay. So again, d replaces the size of the hypothesis class. Okay. 2 says that for any epsilon delta greater than 0, if we take n greater than 64 over epsilon squared times 2d ln epsilon plus ln 4 over delta. We get epsilon accurate learning with confidence 1 minus delta. Okay? So this is, in the previous band we had, I think, 2 over epsilon squared times something. What was it? 2 over epsilon squared ln 2 size of h over delta. Okay? So, yeah, it's a similar thing where d is actually replaced by what? The log of the size of the hypothesis. Okay? And you'll show actually in the exercise that for a finite hypothesis class, the VC dimension is upper bounded by the log of the size of the hypothesis class.
Amigo, I'm sorry, that's so weird, so can you write it more clearly? First, delta out there.
Here?
Delta? No, upper?
Confidence
No,
interval.
inside square. Inside the square.
Here is delta.
Above the n. No.
Here?
More or less. Less. Here.
8.
Fine.
I'm sorry, this is 8. Okay.
And write below this. What is this?
64.
Ah.
Okay. Yeah, some numbers that come up,
No.
ignore the concept. Yeah, the writing is not so clear. So, okay, good. So, again, we're not going too much in detail here, but what I want to basically argue is that once you have the VC dimension and it's finite, okay, you get all the bounds that we had before. The concepts are a bit different, but you know, you have basically d replacing the log of the size of the hypothesis. Okay. Right. And actually, these bounds are a direct result of this. This is just algebra. So the main thing is these two theorems that are not that easy to prove. Okay. Okay. So just to show you how a VC dimension is calculated, I'll give you a few examples and then do some more in the exercise. Okay. So examples of VC. So let's do one where h is function of the type x, well, basically, yeah. Let's do h of x is the sign of x greater than a, where x is in the ring. So basically, x is one-dimensional, okay, and our hypotheses are something like well, let's do w times x. We can also do this. So our hypotheses are stuff like this. So this is plus and this is minus, or this, where this is plus and this is minus. Okay. All right. So essentially, thresholds on the line, where the threshold can be the labeling can be plus or minus on either side of the threshold. Okay. So these are your hypotheses. What's the VC dimension, do you think? How much? What is it? Okay.
No, it's a number of.
Well, let's see. Okay. So for what's pi a?